So I'll do the recording. Okay, I think we are ready to go. Only that I need to find myself. I don't know where exactly we had ended. I'm trying to recall. Guys, I think, of course, if you want to remind me of anything, you can always alert me. But I think we had reached somewhere here, if I recall. Had we reached this part here, guys?
No.
Oh, okay.
Yes.
Someone says yes, someone says no. Now I am confused. I'm getting two different answers.
No.
No.
We hadn't.
No.
Okay, please, as soon as you give your response, you mute yourself. As soon as you give your response, just mute yourself. Okay, so if you hadn't, we need to move backward. And okay, this is where the example started. We had made quite a number of illustrations. We did this, we did that. Then we had said let m equal to n minus 1. I think people still had issues here. There is one guy who was asking me quite a lot about this. I think that could probably have been Wafula, where I would say if m is n minus 1, n is m. I kept insisting on that. Why? I wanted to avoid the multiple substitutions. You can keep substituting all of those. These things are quite lengthy. If you struggle to always recall that your m is n minus 1, but n is m, you can keep making multiple substitutions. Of course, those can cost you time along the way, but they don't bring you any marks in because they are not really part of what we want to assess anyway. Because we want to understand this technique, and then we see how you can use it to solve some engineering-related kind of problems and what kind of problems would qualify. And then we also apply some so-called linear equations. So for those, please mute yourselves. You guys, I think I have to mute all of you, and then what is that? Okay. So what I'm going to do, because I didn't have any control over the noise, what I've decided to do is to mute all of you, because you guys have failed to behave. But there is only one danger to that, is some of you who may have questions may not ask. So what you do, you'll just take note of the question you have, and during the question session, I'll try to unmute all of you and you ask. In the meantime, those who may have questions, you can go into the chat room. You pass your question there, or you could raise your hand. At least if I see you raising your hand, I can quickly come and unmute. Otherwise, I didn't want to unmute you, but somehow some of you are too immature. And you've left me no option but to do what is not very healthy for this virtual class. Okay, I usually prefer people interrupting. You have a question, you unmute, you ask yourself rather your question and you mute. Okay, let's pick it up from here now, guys. And I insist, if you have a question, you can go in the chat room or you could raise your hand. I think you have those rights of raising the hand so that, again, we don't over-stagnate. So last time we had this example. I'll just quickly review some of the steps I went through so that we are all on the same page. Let me just simply go through this, but a little bit pretty fast. So we looked at the definition of a power series solution and rather a power series. And we said that according to the definition, this is what we had. Then we looked at very many other definitions to do with the ordinary points, irregular and regular singular points. We understood when is it said to be analytic and when is it non-analytic. And with all of that we discussed, I also showed you how to actually change limits. And we also applied that in this particular example. And then after that preamble that is all examinable, we bumped into the first example. And we're still going through this example in power. We had some power interruptions, and the one who booked at the session had no control, and we lost the lecture abruptly. So I'm picking it up from there, and we had, after that preamble or the introductory part that is all examinable, we had this example where we said that the power series solution, determine the power series solution to this differential equation here about x equal to 0. And then when we did that, we came through this, we said since you have this, and by definition y is given by that, since this is y prime, we said you can differentiate once. But before differentiating, we said since x is 0, we substituted for this one here. This being 0, we ended up with this one here, which was y summation n equal to 0 to infinity of that. And then we differentiated this once. You differentiate this once, we got this one here. Then after getting this, we substituted into this one here. So on substitution, this is y prime. We are substituting directly into that one there. So y prime is this one here. We substituted, which is this one here. Then we substituted for y, because this is plus xy. So the x is right there, but we had our y, and y is this one here. So when we substituted for y, we got that. Then I had also explained that every time you differentiate this one here, you have to upgrade this one. Y, if you take the first derivative, you have n, you have an n x to the n minus 1. But now you can't move n from 0, because if you start from 0 to infinity, this whole thing would vanish. So since we had taken the first derivative, that meant that the lower limit is upgraded to n from 1 to infinity, which is this one here. Okay, that's why you see that this was n to 0 up to 1, rather up to infinity, and then this is from n equal to 1 to infinity, which is this one here. But we insisted that by definition, since this is this whole series, it is to the n, now you have this one here is to the n minus 1. So for this to be solved, these sums have to be uniform and quite consistent. Otherwise, you wouldn't sum, because it's like trying to add unlike terms. And we all know you cannot add unlike terms, you can only add like terms. So because of that fact, that's why once we have a situation like this, it means that if we are to sum, this summation here must be the same as that summation there. That is 1. Then the power here, maybe I change that to a different color. the power must also be the same. This power here must be the same as the power there. So in this case, we have inconsistencies. You can see that this power here is n, that power is n minus 1. Then here you are summing from n0 to infinity, and here you are summing from n equal to 1 to infinity. So it means that we need to find some kind of consistency with respect to, first of all, the powers of x, and then the sums themselves. If you are summing from n equal to 1, and this is summing from n 0 to infinity, then you basically can't sum up those. So once you have substituted to do this, the remaining task is to generate some kind of uniformity in these sums and then the powers of x. And once you have secured that, you can now go ahead to simplify. Okay, so when we did that, rather after trying to explain that, so I have substituted this, I have substituted that. The next task now was to generate some kind of uniformity with respect to this and that, rather to generate some kind of uniformity with respect to this and that, and then that and that. That is the powers of x. And usually for the powers, we usually insist on, we try to simplify this or to scale it to what our definition actually has. So the sum, we can sum from any number to infinity, but at least the powers we usually stick to what we have in the definition for those powers. So in here, when we had this, the first step here was to try to simplify this. So you can see this x here was outside. We took it inside the sum. So this x was to the power 1. We ended up with x n to the power 1 because you have x to the power 1 and you're multiplying it with the x to the n. So base is the same, you add the powers. That's how this x to the n becomes x to the n plus 1. It's because of this x outside. So that was this step. So after getting that, we said, okay, so how do we proceed? Now we need to standardize or try to make our the powers to the x uniform. So we started here. You can see, first of all, what the first attempt we made was to unify the sum so that we start from the same lower limit. Here our upper is to infinity, the lower is from 1. So since this is 1 and this one is 0, then we are like, can we start both of them from 0? So this was the first target. You can see that in here, you can see that initially, rather in the step before, this was n is equal to 1, but in here it is n is equal to 0. So how did we get there? We started it here, and this one I had already demonstrated. We started here, and how do we start here? You only look at the sum. We look at this power here. And we say, since it should be x to the n, what if we let this to be m? So if you let that to be m, and we say m is, this is what, n minus 1, n minus 1. So it means this one here is going to become x to the m, okay? So since this is x to the m, then it means we have to think about this one here, the n minus 1. But remember, n now becomes m, which m will now take back to n. So it means for us to get our m, since this is m is equal to n minus 1. So it means where you have n here, you will substitute. We have our n will be m plus 1. So you have m plus 1, and then you must look for the new n, and that one will definitely go to 0. So in simplicity, if you have m which is equal to n minus 1, you can compute n. N will be m plus 1. So if you take the m to n plus 1, then you can find the values by substituting what this sum is. So here we are, since it is n moving from 1, this part here. If our n is 1, it means we can get the m. So what would be m? So our m would be n which is 1 minus 1, which is 0. So since it is 0, come in. Since it is 0, what do we end up with? We will end up with yes. This is Uganda manifest. What is next? You pick a copy. Okay, sorry about that, guys. So what I was saying is when you substitute, this is m is n minus 1, but n is 1. Remember, we are summing from n equal to 1. So what does that imply? That m now will start from 0. So it means m will run from 0. So it means our limit, the lower limit has changed. It's okay. The lower limit has changed. Of course, the upper limit will still remain the same. If you change that, you're now starting from n equal to 1. Of course, n, if you take infinity and you substitute infinity here, m will still remain infinity. So it means you're going to run from m0 to m infinity, okay? So, but I say the m is n. It means after substituting the m, you have again to resubstitute it back into n, so that you don't have multiple changes of these so-called would be notations, the powers. Otherwise, from m, when you're changing here, you may again generate a k. Then from k, you may generate a certain I, and it will go on and on. So for those who feel like they are more comfortable doing that, please, you do that, no problem. But me, I will not do that. Okay, so since this is m, it means now our m will run from 0. But remember, in here, we have n and we have an, but now, what is n? We have to substitute for n. We make n the subject in this. It means the n will be equal to m plus 1. That is what we have there. So since we have that, for this part, you can see now the an here has become an plus 1. As I've said, n will be m plus 1. So it means you'll have this is m plus 1. Then you can write this whole step, but after that, you will now say if m is equal to n, then you substitute the m with the n, so that you maintain the original notation that is being used. So for those who may be struggling and they are part of the time taking in terms of comprehending how these n's can be switched back, you can take to m, and then maybe m goes to a certain k, and maybe the k goes to I or j, and in the very final statement, you switch them back to n. Okay, so I said that's why this was an, the an has now become an plus 1. which is am plus 1, but m is n, so it becomes an plus 1, which is this one here. Okay, now in here we had the n. If you look at, maybe I need to change the color, hopefully people are following me. So somewhere here we had a certain n, there is that n there. Again, we get the n from here. If you look at this one here, what is n? N is m plus 1. We have got it here. So since this is n, this n is going to become m plus 1. That is this one here. That is the n plus 1. Remember, it is m plus 1. But I've told you after substituting, you take it back to n. So it becomes n plus 1. That is this term here. Then remember, this was n minus 1, but n minus 1 is m. So this becomes x to the m, which I had written as this. But after that, you'll bring the m back to n, which is xn. Okay. So with that, we have managed to switch or to improve this one by making sure that the lower limit here is the same as the lower limit there. So this moves from n0, that moves from n0. But in doing this, yes, this is a success, but we still have some small problem. What is that small problem? The small problem that can easily be fixed is right here. This one is x to the power n, but this one is x to the power n plus 1. Now that is another setback. Sometimes in fixing one, you create another one. Okay? So since this is x to the power n, but this is x to the power n plus 1, we need this power to be the same. Otherwise, we can't do much here. So how do we do this? The first part is now to change this x to the power n, because remember, by definition, our definition here, this one, it is an x minus x naught to the n. But remember, it was about x local to 0, so the x naught was 0. We ended up with the ax to the n. So we must maintain this one here. This one should be maintained, that part there. So because of that, we ended up with okay. So we've ended up with this situation here. That is this, and then we've ended up with this, and then this one here. So it means we must take this one to x to the n. That is what we are attempting to do here. And by doing that, we are bringing this x to the power n plus 1 to this one here. You can see how that has changed. Now we have x to the n. This is also x to the n. But how do you do that? You simply get this one here, and you say, for you who want multiple changes of these powers, you can now say, what if n, k is n plus 1? Remember now, for you who are adamant, rather resistant to these substitutions, remember we had changed it to m. Now the m will become a k, because now this one would have appeared as a m. But remember, you took it back to n. If you had maintained it as a m, then you would say maybe let now k equal to that one there. So if k is equal to this, it means that now you are going to have x to the power k, which k is m, and which m goes back to n. I'm saying this to insist Mr. Wafla. I think it was Wafla who was getting issues with these powers. So if it is x to the power n plus 1, but now the n plus 1, or which was m plus 1, is now k. So if this is k, then we need to get the new lower limit of n based on this change here. So since we have this change here, it means now that our k the k, remember now here n is 0. It means k will be 0 plus 1, which is a 1. It means now here our sum will run from k is equal to 1 all the way up to infinity. That's why you see that in here we are summing from n equal to 0, but in here we are summing from n equal to 1. That change comes from here. It was n plus 1, and now it has changed to 1. So this would have been k equal to 1 to infinity. And because of that, we can make n the subject here. What would n be? N would be a k minus 1. This one here. That's why you see that here what you had as n, I think I need to load. Okay. So you can see here that what we initially had as from this, we have an. You see this an here? This an now has become an minus 1. You can see that one there. This is this one here. How? It was when we changed this one to k, this becomes now a k minus 1 because the n is k minus 1, but k is n. So you get this one here. I insist as I continue, those with the questions, you can keep sending them into the chat, guys. Don't be left out. If you have questions that are burning, please utilize the chat and you write your questions. I can find them there. Otherwise, I'll unmute you and you ask your questions. Or you take a note of your questions as we go through. Okay. So since this is the case here, we now have an minus 1, and that is n. We have now succeeded in this step. We have succeeded in having x to the n, and also here we have x to the n. I emphasized the things you should worry about. That was the power to the x and then the limits of the sum. So here now, x is to the n, this x is to the n. We are remaining with one other small problem. In our attempt to take this to the n, which is now k, for those who don't want to substitute back, now this x would be to the k, and this is to the m, but remember, if this is to the k, but this one is to the m, you still have a problem. It means now the m would also have to be taken to n. So the only small problem we are remaining with is now the limits. Here we had fixed the limits, but in an attempt to fix the limits, we ruined the power here. Now we wanted to fix this power issue. Yes, we have fixed it there, but again, in an attempt to fix this one, we generated another problem here. That this n which starts from 1 is not the same as this n which starts from 0. So once you reach here, the last part is quite even easier than the previous one. Since this is n is equal to 0, we can just upgrade this one here by simply punching. If we take this one, just concentrate on this, guys. So if I only choose to substitute, remember n runs from 0 to infinity. So if I simply choose to substitute 0 only, if I substitute 0 here, it means this is 0. I'll have a 1. I'll have 1. There is a multiplication here that is times my n is 0. So I'll have a 1. Then x is 0. This will give me x naught. So this one comes when I substitute n is equal to 0. So I have a1, since n is 0, this is x is 0, this is 0, I have 1. Then once I have that, I can now, for n is equal to 1, I can now simply sum this. So I have this, but remember summing, you add. Since I've substituted 0, I can add here. So I add this to the sum. Now this will be from n will equal to 1 to infinity of this same term, which is n plus 1. Moment. This will be n, but I told you to come with the person of QE. Yeah, okay, you look for the one of QE. You come. Yes. So this is n plus 1, and n plus 1 into again n plus 1. This is x to the n. But remember now, this n runs from 1. Why? We have already substituted n running from 0. So once you substitute, because this one runs from n is 0, you have 1, you have 2, and it goes all the way up to infinity. So from this huge domain of numbers that you could pick, and then you substitute in there, we've chosen only 0. If you choose only 0 and you substitute into this one here, that would give us this term here. The one we got there, this is a0 plus 1, which is a1, which is that. This will become x0, which is this, plus we substitute the next one. The next one would be, the next substitution would be this one here. So since it is 1, we can then simply sum, and we say this plus that sum. So that once we have that sum, then we realize that this n equal to 1 will be the same as that n equal to 1. And that is what we have done here. You can see this step, the one I'm highlighting in blue. That is how we ended up here. Because you can see the term I have here, the 1 times a1 x to the 0 is 1. Then you have a1 times that, which is just this a1. Then we sum. And how do we sum? We sum from n. But remember, in this case, this is n to the 1, n to the 1. So we can combine this with this. Hopefully we are clear here. So I am combining this with that. Remember, the n's are the same, and the sum, we have the same limits from 1 to infinity. So in that case, we can combine. The sum here is the same as the sum there. You need probably to clear this a little bit. So I am saying we can combine these ones here. Since we have this, it means you consider this one now to be running from 1. Assuming this one is running from 1, this is to the n, this is to the n. The x to the n is the same as the x to the n. So we'll have just the sum. This will be n running from 1. This is to infinity. And we are saying the sum and that sum, they are the same. So what do we have as something different? But remember, we had already substituted 0 here, and we got a1. This is plus. So we need to separate here. So what do we have? We have something like this. If I use a box bracket, we'll have n plus 1 into an plus 1. This will be n plus 1, close brackets, into an plus 1. This is an plus 1. That is this part here. This xn is the same as that xn. So we add to this one. What do we add? We add an minus 1. This is plus an minus 1. We have added this one with this one here. So you close this box bracket, you'll get here x to the n. That is this step. This step here is exactly this one here. This one. This simplification in blue comes to this one here. So since it comes to that, since we are summing from n equal to 1, we can now utilize this. We already know in here you have A1, and here we are saying we can equate the coefficients. Equating the coefficients of x to the 0 gives, so we have this and we have that. So when we say x to the 0, taking x, of course, this one cannot run from 0. Why? This n is running from 1. So for x to the 0, it means you remain with this one. This is the one we got when we equated, when n was 0. So remember, it is x to the n. So when n was 0, x to the 0, which was 1, it gave us a1. So it means this a1 will be equal to 0, which is this one here. And then we look again for this coefficient here. That is this coefficient, the one I am highlighting, that one there. So what would this give? Since we are equating it to 0, remember when you equate to 0, we go to this. Now when you take x to the 0, here it will give us a 1. When you simply say coefficients of n to the 0, this one was x, this is the same as xn. Of course, it had some n, there is a 1 there. So when you take to the 0 and you take to the 0 here, you remain with this term, because x to the 0 here would give you 1. You remain with the whole of this, which is this one here. Is that okay? So if you get this and you substitute, when you substitute, you get, rather you have now two equations. You have the a1, which was equal to 0, and then you have this one, which is n plus 1, then an plus 1 plus an minus 1. But from this, we can make our an plus 1 the subject. Remember, these are like what we call recurrence relations. So in this case, what would be our situation? Remember when we added and we changed this one, I had the greatest power. That's why you see this is an plus 1. Then when we had upgraded it to 1, we took it to 0, and we ended up with this. So you make that one the subject, which is this one here. That is that term there. When you make that term the subject, this will go to the right. That is the minus 1 over an plus 1, then an, or you can simply write it as a. This is n minus 1, then the whole thing over n plus 1. This whole thing is negative. So we just make this one the subject. And if you do that, that is what we are saying, that if you, this one follows the concept of recurrence relations, which are more studied when you're dealing with the difference equations. You have a lot of this recursiveness. So if you make this one the subject here, you end up with this statement, which I have just demonstrated. And once you have this, remember the n had already been fixed for 0. I think you guys, you still remember that. Remember when we said equating coefficients of powers of x to 0, this part here. In here, we said equating powers of x to 0. We have already dealt with that 0. That's why in here we are saying that n must run from 1. Because if you run this from 0, that would be a fundamental mistake. You'd be again substituting what has already been catered for. In our attempt to simplify to this step, we had already substituted the n equal to 0. That's why we insist that in this recursive expression, we substitute for n starting from 1, and we can go all the way up to infinity. Okay. So what does that go to? We can now try to substitute a sum of these values of n into this formula here. And if you do that, what you get, if we do that, we are substituting into this one here. So simply substitute values of n, starting from 1, we insist on this one here. We have already catered for the 0. If you take n equal to 1, that is this first one here. So you take in 1, if you throw a 1 here, this becomes a2. That's how this one becomes a2 here. Because if n1 plus 1 is 2, you get a2. Now what about this one? N is 1. If n is 1, you'll get minus a half. Remember the n is 1 here. So that is minus a half. And what is n? This n is 1. So if it is n1, this n is 1 minus 1. So that will give you n naught. But remember, from up there, we know that n naught is 0. So when you substitute in here, remember our n naught is 0. So when you substitute in here, that will definitely disappear. So it means you will end up with the an a2, which is 0. So here, this you can easily say that this is equal to a 0. Why? Because of this n naught. Remember, in the previous example, rather in our demonstrations, we said that equating the coefficients of x to 0 gives a1 equal to 0. Not n naught, sorry, this is a1. I had made a mistake. It is not a1, but rather n naught. N naught is 0, not a1. This is wrong. N naught is not 0. It is a1. Clear this here. So we got a1 as 0. So when we have this, it means our a2 is equal to minus a half n naught. Then we substitute n equal to 2. When you substitute n equal to 2, this one, where there is n, you throw a 2, this will be minus a third. That will give you minus a third. Then what is n? N is 2, this will be a2. But what is a2? Our a2 is minus a half, so this is minus a third. We have got a2, but a2 is here from the previous one. A2 is times minus a half. That is a naught. And when you do that, you'll get minus 1 over 6 a naught. And e. What am I doing? This one gave me a 3. I think I'm making again another mistake here. We have n is equal to 2. You throw here 2, that would give you a 3. Equal to. So this gives you a 3. But what is our a3? So this is a3. A3 is 1. This is a third. This is a2. Oh, okay. We made a mistake here. This is a1. Sorry. I think my substitution came in from here. That's why I made the mistake. This is not a2. This should be a1. This one here. The mistake is somewhere. The mistake is here. When I substituted, I was supposed to substitute n is equal to 2. When I came here, I substituted n is equal to 3. So when you substitute n is equal to 2, that is 2 minus 1. That will give you a1. So this is a1. But remember, A1 is 0. Since A1 is 0, this whole thing goes to 0. So ignore that. Then we go to the next one, that is n is equal to 3. N equal to 3, where there is n, you substitute 3. This will be F4. Once you get F4, this is the 3, that will be minus a quarter. Okay, and this will be n is 3, this will be A2. But what is A2? The A2 is the A2, or A2 is minus a half n naught. So this is times a half, but this is negative. That is n naught. Minus minus will give you positive 1 over 8 n naught. And that is this one here. Then you can do the same for n equal to 4. It will give you F5, which is 0. You do the same for n equal to 5. It will give you, and you simplify, you get a minus 1 over 48 n naught. So if you get that, you can now proceed. How do you proceed? You proceed to substitute. We have these ones. Now we can proceed and substitute into, remember our expression, we have it here. That is this one here. If you expand this, you'll have A0, A1, A2. You keep, so here you have A1, A2, A3, A1 goes with the X1, A0 with the X0, and it can go on all the way up to infinity. So we are substituting into this one here. If you do that substitution, you will end up with what you see here. Remember, A1 will give you what we got as A0, then we have A1, we have A2, A3, all the way up to A infinity. So when you deal with this, this is our statement. We have substituted. When we substitute, you get this one here. So if n is 0, you have n0. This is x0, but x0 is 1. So you get this one here. Then if n is 1, you have a1 x to the 1, which is x. If it is 2, that is a to x squared 3, a cubed x cubed, all the way up to f5. Then we substitute in these ones here. So when we substitute, what do we get? A0 remains A0. A1, we got our A1 as 0. Remember the A1, we got it as 0. A1 was 0. So it means when you're substituting, this A1 will be 0. A0 remains as A0. A2. Our A2 is actually, our A2 is, this is where we had our A2. A2 is minus a half A0. So where you have A2, you'll substitute minus a half. This is minus a half. A0. Then we have A3. A3 is 0. This is 0. Then we have F4. F4 is an eighth. This is an eighth of A0. And the F5, we have minus 1 over 48 A0. So we substitute this into that. When you do the necessary substitution, you can see the A1 is not there. That is why you don't see X here. Then the A3 is also not there. That's why you see here, there is no X cubed in here. You don't have any X cubed. So we ended up with factorizing the A0 out. That would be A0 into 1 plus a half X plus 1 over 8x to the 4, then this is 1 over 48x to the 6. And you can confidently conclude that this one here is of course, the A naught can be established under some given kind of under given conditions. Okay, so A naught, this one can always be defined. Given, remember when you have what you do call this one is not, this is, if you have an initial value problem and you have some initial conditions, then you can actually establish the A naught, this one here. Because this one here is what we call the general solution. But if you have conditions and you can end up with the specific solution and the A naught becomes something else. Okay, I think I'm going to take this moment. I unmute. Those with questions can ask. Maybe I first go to the chat. There is a question. And then from the chat, maybe I start with these people raising their hands. Madam Nakianze has her hand up. Let me first of all try to unmute now all of you. And then I'll hear from Madam Nakianze. Right, where are the participants? Okay, so you can now unmute yourself. I'll start with Madam Nakianze and then I'll go to the question in the chat. Madam Nakianze, you had a question. Can you unmute yourself and ask?
Excuse me, Doctor. The question asked us to find the power series for a certain differential equation, but I'm seeing the series we have is only for y. So have we answered the question or?
Yes, but we are solving. Remember, we are solving. We are finding a power series solution of this of this differential equation. You remember what we did in linear, oh, sorry, not linear algebra, but rather engineering math 2. We did the is. We did some differential equations and you'd be given an equation like this and then you solve. When you solve for this in y. Since this is dy dx, then you have xy, this is 0. So here we want to find the power series solution of the differential equation. So it must be, you solve for this in y, but remember it is dy dx. So definitely your independent is x and the dependent is y. And that's what we have here. That's why we have y, which is equal to this in terms of x. Madam Lydia, are we together? Madam Lydia, oh, sorry, Nakianze. I don't know why I'm picking the name Lydia. Maybe I saw some Lydia there. Okay, she's not responding. Hopefully she has understood me. There is a question. I don't know whether it's a question. How do we know the value of n on which to stop? No. For example, here we went up to n is equal to 5. Remember, n runs from 0 to infinity. So if you go up to n is equal to 5, that is good enough. Remember, some values of a may go to 0. Is that okay? So if you can't just stop at n is equal to 1, since this is a series, and you can see the nature of the solution. This one here is indeed, we are simply summing up. Of course, in our attempt to sum up, the simplification here generates a negative, and you have that negative, but this is simply summing here. So where do we stop? You could stop anywhere, but it is better. Sometimes the question may be specific, that you sum maybe up to n is 6 or up to n is 7. That helps to have uniform consistent answers. But otherwise, if it is open, one may stop at N6, another one may stop at N7, another one may stop at N5. But the minimum could be N equal to 5, minimum. If it is not open, rather if it is not specific that as you deal with this pass, there is a kind of computation that you should go up to a certain value. Given that some of the values of the N's can go to 0. If you go up to N is equal to 5, that is relatively good. Okay. I think there are more questions in the chat. Isn't F4 a positive? I don't know. You can check it out. The mistakes in the notes, those are your responsibility. Someone is wondering whether F4 is not a negative, but we can check that out very fast. Where is our F4? F4 is somewhere here. Isn't that a negative? Easy to check. This was N equal to 5, so our N is equal to 5. That is N5 here. So what will that give us? That would give us a -1/6. We can check that out. This will be what? N is 5, isn't it? So if it is N5, this would be A4 because it is 5 minus 1, which is 4. But what is F4? F4 is 1/8. So you have -1/6, and you're multiplying that by this one here. Remember, it is F4. F4 is the F4 is here. So F4 gives me 1/8 N0. That is 1/8 N0. Whoever was asking that question, our answer is correct here. Whoever raised that concern, 8 times 6, that gives you 48. The negative, you can see the negative is here, which is that one. It's not positive, right? Okay, I think there are no more questions. I don't know whether there are hands that have been raised. I think the questions are over. Can we continue? Let's continue. And we look at, maybe there is another one. For N is 3. I don't know what this one is saying. This is again Lydia. Okay, please you follow that up. You can go and you check N is equal to 3. I don't know what is happening. I checked this last one. N is equal to 3. Okay, N is equal to 3. If N is 3, that would be -1/4. Okay, that is N is equal to 3. N3, this is F4. I think that is what we are getting for now. N3, that is 4. This is minus that. This is N. That would be A. N3, that would be A2. But what is A2? A2 is here. A2 is 1/8 N0. So this is -1/4, then A2, which is 1/8. I don't really understand what you guys are asking. I think this is also okay. Okay, I think I'm ending the questions there. I need to continue. Okay, the mistake is in the solution of y. I don't know what the mistake is. Oh, the coefficient of x4 is positive. Okay, you go sort out your confusion. Because even in the questions you're asking, when I try to revisit, everything seems okay. Right, that is that. The questions I've tried to answer, but all you're asking seems to be contrary to what I have. Let's continue, guys. Let's do one more example in the remaining time. And in this remaining time, we can try to do another example, but now in this example, I'll be a little bit fast, given that you already know what is supposed to be happening now. Okay, so this is, I'm going to leave you guys unmuted on assumption that we won't misbehave. Otherwise, if I'm sure I'll misbehave, then I mute you again. Okay, so I'm assuming you'll all behave. So I'll leave you simply unmute yourself. You ask what you want to ask, and then you mute again. Right. This is another example. I can go through this, given that I've done the first cumbersome task. I think this one won't be too much of a problem. So what we have here, similar example, only that now here what we have is second order. That is the only difference. The first one we had was a first order. So this time around, what we have is second order. Okay, someone insists the coefficient of x to the 4 should be a positive. Okay, let me check that out. There is someone still having some issues with my answer. The coefficient of x to the 4. Okay, let's check this out. That is this part here. Okay, how did you arrive there? That was from this part, x to the 4. Someone is complaining about the negative. I didn't pick whoever asked the question. There was a question in the chat. I didn't pick the name of the person. Let me see. This was who? This is Nisima, Charlotte, I think. Charlotte says the coefficient of x to the 4 must be negative. X to the 4 comes from here. What are we dealing with there? There we are dealing with the F4. Okay. F4, according to our F4, F4 is 1/8. Isn't this the n you look at 3 someone was complaining about? I think that was the n equal to 3, and that is minus 1/8 n naught. Okay, we need to check from our formula. So these are the two things we need, because F4 comes from here, then you have that, you have that. Perhaps I need to check again, but I think you could easily fix that, you people. But I can simply go through, because I remember someone asking about n equal to 3, and it didn't. Okay, here we are again. N equal to 3. 3, that would give me 4, 3. This would give me minus a quarter. Okay, and this would be A3. What is A3? A3. A3, no, not A3, but let's see this. We have, if n is 3, we have F4. That is that one there. So it is a 3, we'll get minus a quarter. That is minus a quarter there. And then this will be A. N is 3, that is 2. So what will this simplify to? It's minus a quarter. We multiply this by A2. But our A2, what is our A2? Our A2 is minus, our A2 is minus a half N naught. I think that is where the problem is coming from. This gives us a positive 1/8. Positive 1/8 N naught. Okay. I think you're right there. That should be a positive. That should be a positive. This will be positive N naught, 1/8. So if that is the case, guys, unmute yourselves. Unmute. If we have that, that is N naught. This should be a plus here. Okay. So what we have is a plus somewhere here. That is a plus, and this is a plus also. I think you are right there. So that should be a plus. That is the A naught. This one is plus. And this one is also a plus. Okay. I think that is, we are good to go there. Okay, someone says, I think you should unmute, and someone, but I unmuted you, I thought so. That is still Madame Lydia. I think I had unmuted you people, if I recall. Okay, I think I can continue. Madame Lydia, I think I have worked on your problem now. Okay, let's look at one more example. Let's just look at one more example. And in this other example, I want us to look at So there is example 2. Yes, guys. So let's look at example. Let's look at example 2 here. So solve the differential equation. This is the second order by power series method. Okay, the beauty about this one, we can really move faster because again, it is x equal to 0. Maybe this time I can, someone said, I think you guys, you can unmute yourselves. I remember deactivating what I had done to silence the background noise from you. I think you should be able to now unmute yourselves. Ask all to unmute. Yes, you can unmute yourselves. You can unmute yourselves. Raymond, can you talk to me? Raymond, is he still there or is at large? Mute, allow participants, sound. No, we are unable to unmute. Yes, Cassidia, I have seen you are unable to unmute. Let me finish this example. You will be able to mute rather to unmute. Okay, example 2. This example 2 is similar to what we have said, what we have done. Why? Someone is asking, this is a Rumba calling, that is it possible to convert the index of n directly without showing? But that is what I was trying to show you the other time, and people were making noise that m is n, n is m. Yes, you can, so long as you are sober and you don't make mistakes. I'm talking to Rumba Collins. Yes, you can, but you make sure you are steady. If you are not steady and you have a little bit of limited concentration, then you could mess up the whole thing. But you can really do it. And that's what I was trying to avoid. When I say the m is n, but people kept asking you, at M is N, at N is M. I said, I didn't want to be part of your confusion. That's when I said that, okay, you can do M. If you are tired of M, you go to N. You can keep those multiple substitutions, but they will not earn you any grade anyway. So as you practice, I'm sure you'll perfect and you'll comprehend the concept better. Okay, so let's do, let us comprehend this. The students are complaining that there is a lot of noise in my background. Yes, apologies, my dear students. There was some saturation in the background of my Zoom room, but I think now you can hear me clearly. You must understand I am running this Zoom from my office and I am sharing an office with a colleague. So once in a while, you may hear a few interruptions. Don't mind them. Concentrate on the shared screen. All right. So our number 2 here, it's not really different. The only difference is a minor difference. Is this is second order. The first example we did was first order. And of course, this is also about x is equal to 0. So there is really nothing much here. Same story. What is that same story? We let y equal to that. This is by definition, but remember it is x minus x naught, 0 and the whole thing to the power n. So since our x naught is 0, I explained this in the preamble. That is when we introduced ourselves to the different types of singular, points, irregular, and the ordinary. We explained that x naught. So from what we did, we can now confidently, and what we've discussed today, we know this is second order. We differentiate twice. So we have y, which is that. We have y prime, which is this. And we have y prime prime. Be mindful that for each derivative, we change the lower limit. For this, the limit was running from n is equal to 0 to infinity. But the first derivative, now we run from n equal to 1, because when you differentiate this x to the n, you have this n a n. So we can't run from 0 because that n will make this entire series sum disappear. So this now n runs from 1. And when we go to the second derivative, remember this n comes there. So you have n minus 1. And if you throw there 1, you'll have 1 minus 1, which will be 0 in this one here. So it means we must now, our lower limit should run from n is equal to 2 to infinity. That is now one key difference you have to note in comparison with the previous example. So in this one here, we are running from n is equal to 2 to infinity. Why? Second derivative. It brings in this term here. If we maintain the 1, which was here, you have n into n minus 1. This n minus 1 would make this whole expression. So we move from n equal to 2. You people mute yourselves, otherwise I'm going to mute all of you. Okay, so same old story. We can now pick some speed. I think we are all good to go. So once we have this, we substitute. We substitute the first derivative, the second derivative. Actually, only substitute the second derivative. We are substituting into this one here. Our second order differential equation. So the y prime prime takes on this. That is this one here. That is that value. That rather this expression here. That is the y prime prime. But remember, you have x squared y, this one here, which is this one here. Okay? So since we have that, we have this and we have this, we can simplify this further. How do we simplify this further? This one runs from 2, so we are maintaining this is the same as that. The only thing we have worked on is this one here. This is x squared, sum from n is equal to 0. We take the x squared inside the sum. So this is x to the n. And then since we are taking this inside, you have x to the 2. Base is the same, add the powers, those are indices. You end up with this sum, n0 n x to the n plus 2. That is this one here. Okay, that one we are good to go. So now we are saying, this is what I've been emphasizing. Now when you look at this here, there is only a few small problems. One, first of all, I told you, you must make sure that when you are summing for uniformity, I told you you cannot add terms, unlike terms. We only add the terms which are similar, okay? So since we can't add unlike terms, this sum runs from 0 to infinity. This one runs from n equal to 2 to infinity. We can't add up these two. So the only way we can add is for these limits to be the same. And then according to our definition, this should be x to the n, but this is x to the n minus 2. And then this is x to the n plus 2. So we need some work. We have some work to do here. One, limits should be the same, and then this and this should also be the same. There we'll be able to simplify this. So how we deal with this fix in steps. So there is a guiding statement there. We are saying that we put the series under the same powers of x by letting this one. So what are we doing? We are first of all fixing this one here. Now we go back to the same story in the first series. So how do you do that? You can see in the first series, that is this one. So if you let n minus 2, if you let m equal to n minus 2, that is m equal to n minus 2. That is this part here. But my n, my m, I'll later make it again m. So m is n minus 2. I think m. Please mute yourselves. Otherwise, I'm going to unmute you. You people. Kasirie Henry, can you mute yourself? This is the man who was complaining about him being unmuted. Kasirie, mute yourself. You people who keep unmuting, you really distract the lecture. Okay. So we have m, which is n. This is, you see now Kasirie has put me off track. What was I saying? I think we're trying to convert this one here. So we are saying if m is n, this is minus 2. So if m is n minus 2, for this one here, this part here, it means when we remember our sum runs from 2, so it means m will run from 0. Remember this n, we are running from n is equal to 2, so when we throw a 2 here, 2 minus 2, that gives us a 0. That's why this n minus n running from 2, it has become n running from 0. Remember when I say m0, if m is this, then after I can take it back to n. For my friend, was it Irumba? I think it was Irumba Collins. I give you a go ahead that you can take it once if you are sober enough and steady to avoid the mistakes. Yes, you can do it in one go. But if you are a little bit of a time taker, or you are a little bit slow in comprehending that concept, then you can go stepwise to avoid the mistakes. Okay. So, please repeat yourselves. People are becoming impossible. The participants, today you are really becoming impossible for me. Okay. I think now you've left me no option again. Let me just mute all of you. I will try to unmute you again. Okay. So that's what we have. So since we have that, and we have converted this to this, we have now n, which was running from 2, it's running from 0. Now we have this one here. How do we get this? Remember, we have said m is n minus 2. If m is n minus 2, then the question is, what is this n here? The n now, we make n the subject. N will be equal to m plus 2. So what does that mean? That means that this n here, that n there, it is going to become m plus 2. But remember, after taking m, I will again take it back to m. So that's why you see that this n, which is m plus 2 here, it is now what you have from here. You now have it as this one here. That is that. I think we are clear. Then we have this n minus 1. So I want us to deal with the n minus 1. So here you have, which color do I use now? Maybe I use green. Okay. Now we have this one here, which is n minus 1. But what is this n minus 1? Since n is m plus 2, it means I'll have m plus 2. Guys, I am substituting for n here. Then minus 1, I have the minus 1. What do I remain with? I remain with m plus 1. It means what I had as n minus 1 is going to become m plus 1, this one here. So this part which we are calling m plus 1, this one here, is what you have there. That is this one. Hopefully you guys are following. Now this was n, but you know n is m plus 2. This m plus 2 again is what is coming here. You see, this is n plus 2. Remember the m, you will substitute it back into n. That gives you this capacity here. And then you have the n, but remember the n is m plus 2, which is this one. I think you have understood that one. So if that is the case, we now have this running from 0, and we have substituted everything there. What does that become? It becomes this. Now, we have the second part. The second part is here. So that is for the first one. Guys, I think you've got me here, those who could be following. But we also have the second part. So if I clear this a little bit, now we have this part here. If you look at this part here. Now for this, we will let m be equal to n plus 2. But remember, if you let this be m, which is n plus 2, what is n? N is 0. So it means m will run from 2. Why? N is 0. N here is 0. M runs from 2. That's why you see what was n equal to 0, it has become n equal to 2. I think we are clear there. Then what is n? If I make n the subject here, n will be m minus 2. So since it is n, now it means that this n here, this small n becomes m minus 2. but m is later taken back to n. That's why you see what we have as n here. This n becomes n minus 2, this one here. And since n plus 2 is m, this one here, but m is later taken back to n, this whole thing becomes n. Oh, good, 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 good. We have now finished this one. Now we have a small problem. The problem is very small. What is the problem? Since this is x to the n, this one is also x to the n. The only difference is in the limits. This one runs from n equal to 2. This one runs from n equal to 0. So what do? You cannot scale this one down, because when you scale it down, as in you take this one to 0, if you take this one to 0, then you are going to bring back this problem here. Is that okay? Remember here it was 0, but n was plus 2. So the best is you upgrade this one so that it matches this and it goes to n will equal to 2. How do we do that? We know that n runs from 0, 1, 2, 3. Zero, 1, 2, 3, and it can go on all the way to infinity. Okay, so since n runs from 0, 1, 2 all the way, so we can deal with only one thing. We can substitute for n. We can take these first two here. That is the 0 and the 1. Then we leave it to run from 2. By leaving it to run from 2, it will now be similar to this one here, if this one is allowed to run from 2. So what would it give us? So it means in here, where we have n0, when we throw in a 0, this will be a 0 here. It will give us a 2. N is 0, this is times 1. N is 0 here. This will give us a2. That is times a2. N is 0. It will give us x naught. But x to the 0 is 1. Here, it will give us x to the 0. So you simply remain with the 2, a2. Always off. MTN. Okay, so you guys. So you have 2a2. Okay. Okay, Irumba has backed out. All right. As he backs out, for us, we continue. So we have 2a2. This one gives us 2a2. And since we have 2a2, that is for n. Of course, this is 2a2x to the 0. So that one is already dealt with, but x to the 0 is 1. So we have 2a2. That's what we have up there. Then we substitute 1. When we substitute 1 here, what do we have? We will have, this is a 3, this one here. When you substitute n is equal to 1, that will be a 3. We multiply a 3 by a 2. Hopefully we are together, guys. This will be a 3. This will be a 2. 3 times 2, that will be 6. So this one will be plus 6. This is 1. This will be 6, a 3, because if n is 1 and you add 1 to 2, that will be 6, a 3. Hopefully we are together. And remember, this is 1 and this will be x. to the 1. Hopefully we are together. Then we will say it is now this one plus the sum. And now n here will run from 2 to infinity of that whole term there. Then plus this one here. And then what we get there, we add that one. All right. So if you do that, it gives you 2a2. That is this one here. I think you can see me here. The 2a2 is down here. Maybe I change to this color. Then I remove this one. And there you go. So we had the 2 times 1. You can see this 2 times 1, which is 2a2. That is this one here. Then we had the 3. This is 3 times 2 is this one here. 3 times 2, then a3. That is the 3 times 2 is the 6a3, which we have here. Then I told you plus n is equal to 2 to infinity, which is this one. That is this new sum now. Plus the old one. This one here is that one there. Okay. So if we get that, now we can continue. If you get that, you can continue, and that gives us this, and then, oh, okay. We summed for n equal to 2, which we have just got. We got this one here. That is the 2a2, which I demonstrated, 6a3x, then plus this thing. This one, you simply collect the terms. Remember now, if you look at this, guys, if you look at this keenly, you realize now that this is this limit is the same as that limit. Okay? And then look at the powers. This power here is the same as that one there. So now we can comfortably add these ones. The limits of the sum are the same, and the powers here are also the same. They can now be combined together, and that's why you see we factorize out. We have the x to the n out. Why? You can now simplify, since we are summing from n equal to 2. That is this one here, and this is the term you have, the n plus 2 that, and then you add that one there. So that is what we have there. Okay. Isn't the coefficient of S3 negative? I don't know. I have not yet reached there, but you will fix them. Someone was asking whether the coefficient of S3 is not negative. I cannot plausibly comment on that, but I think you will do the needful. So once you reach here, we are now going to simplify this. And we are saying if you take the coefficients of the powers of x, now remember, when you take the coefficients, so when you take x to the 0, we had this term here. For you guys who may remember, this one was when we took x to the 0, we got to a2. That is on the left-hand side. What do we have on the right-hand side? On the right-hand side, we have 0. So you have 2a2. That is equal to 0. Because on the right, this will have 0, therefore a2 is 0. A2 becomes 0. That is that one. Then from x equal to 0, we go to x to the power 1. What is x to the power 1? X to the power 1 will be this one here. For x to the power 1, we have 6a3, that is 6a3. But what do we have on the right-hand side? On the right-hand side, again, we have 0. Okay. But after the moment, we are not big. The thing was off. But it was off. Okay. Okay, so we have 6a3. On the right-hand side, we have a 0 this way. So this is 0 again. So what happens is again A3 is 0 in that case. So remember, we have remained with this term here. It means to deal with this term here, n must have to run from 2. That's why we are saying in this case, when we simplify, we say that n can only run from n is equal to 2. And for this one here, of course, an plus 2, this will give the highest. So we make this one the subject. In terms of recursiveness, we make an plus 2 the subject. That is this one here. So since this is 0, remember this one is a plus. When it crosses, it becomes a negative. That is why you see you have this. You can simply see negative. This can simply be negative. Can simply be negative this over that one if you want, or you can write it like this, no problem. But you could even take it as an over that. But remember, this an keeps changing, because if n is 2, you have n naught. That's why we usually take it out of the fraction. So when you make an plus 2 the subject here, you will get this term here. Is that okay? So if you get this one here, that is when we are taking the powers of x, remember, and for x to the n, what does it give? For x to the n, you only have this term here. For x to the n, the other side, there is nothing. So if there is nothing, we equate this thing to 0, and then we make an plus 2 the subject, which gives us this. And from that, we have now a lighter task ahead of us. What is that lighter task? We try out. Someone in the previous example said we should go up to n look at what? I've already told you that n runs from, in this case, it runs from 2 all the way up to infinity. So, but we have already looked at 0, we have already looked at 1. So you could go up to n5, you could go up to n6, you could go up to n7. Right. So when you do that, I'm not going to take now much on that because we have just demonstrated this. Do the necessary substitutions. Simply pick. Remember, you must start from n greater or equal to 2. So if you start with the 2, you substitute here, that will be 2 here, that is a 4, this is a 2, you have a 4 times 3, that is going to give you 12. That is this denominator here. But what is it 2? This is 2 minus 2, that is minus 12 n naught. You get this one. Then you take it to 3. If it is 3, this is 5 here. If this is 5, this is 4. 5 times 4, 20. But if it is 3, this is a3 minus 2, it gives you a 1. And I think we got a, was it a1 as 0? No, a1 is not 0. That is the 1 over 20. You see there is a 1 over 20 here. Minus 1 over 20, a1. When you get n4, you continue like that. You end up with these things here. Then what do? You substitute these into this. And when you substitute and you do the needful, you end up with this one as the answer. That is the answer there. Okay. I will unmute if people have questions, then they ask. If they don't have questions, we continue. All right. What do we have? I want to unmute you people. Those who can ask questions in the chat, you go in the chat. Okay, where are these people? I can unmute you. Right. I think you can now unmute yourselves. You can now unmute yourselves, but do you have a question or you are trying to check if you can unmute? Okay, since there are no questions, I think everything is now okay with respect to that example. No questions, there is nothing in the chat, there is nothing coming out. Questions, guys, questions? It seems some of you are starting to enjoy these virtual classes because you are understanding things very fast, which is good for you and good for the university as well. Questions? Okay, there is one in the chat. We are understanding. This is the comment I want, Joel Okanava. Right, let us do example 3, the last example. We conclude with this example since you have understood that one. I'm now going to mute you again. Maybe this time people will behave. I can leave you unmuted. Okay, let's just do now. The more examples we do, we pick speed. So now in this one, we are going to pick even more speed. Since you are now okay. Okay, there is example 3. Let's conclude with this example, guys. Let's conclude with this example. This is the last one we are doing for this session. Okay, in example 3, but I think I can omit this one. Same story, only that. Okay, maybe there is something small to change, especially given the coefficient of y prime prime. We can probably try to deal with this one. There's some small explanation there. Okay, same story. I'm not going to take long on this. Why? Everything is the same. I'm going to dedicate more effort on the 2x plus 1, this term here. How you deal with it, just this one here. The other things. So by definition of a power series, we have that sum running from n equal to 0 to infinity of n x minus x naught, the whole thing to the n. So since this is about x equal to 0, the x naught goes to 0, you remain with this, differentiate this twice. If you differentiate that twice, you get these ones here. All right? And once you get these, you substitute. The substitution has given us this one here. You can see the substitution. So how do we deal with this? We have a 2. We can first of all expand this. 1 times this sum, it will give us this sum. Then we have 2 times this. So we have a 2 out here. Okay. What we are doing here, guys, is we are expanding. Okay, here you go. We are expanding this one here. This we have this sum n into n minus 1, n x n minus 2. So we are going to expand this one. When you expand, you'll get 2x. This is into the sum. Hopefully we are together. Which sum? This one here. Is that okay? So we take the 2x times this, then we have the plus, but this one times that, you get that very one, you bring back that sum. But now this 2x, it has this x here that we have to take inside. That's why you see here, you only see it as a 2. The x, this x here has been taken inside. How? This was x to the power n minus 2. So we have x to the power n. We have x to the power n minus 2. That is this one here. But remember, this is x. So this x is to the power 1. When you multiply this to the x to the power 1, base is the same. You are going to deal with this. Since this is minus 2 plus 1, you get minus 1. That is the new power you are getting here with the 2 outside. So this x has gone in. Hopefully we are together there. Then remember we had 2x plus 1, but now the plus 1 here, you multiply this by that. We bring back that sum, which is this one here. Then it is that sum. Then we bring back this one here, which is this one, and then this one, which is that one there. Okay, I think there we are good. So when you do that, we have this one here. And once you reach this, the story is the same now. You can see what we have here. What we have is a buffet of very many things. We must take this one to n. We must take that one to n. And this one must also go to n. You first fix those ones. After fixing this is n, this is n, this is n, we will fix the lower limits. The upper limit will always go to infinity. So first of all, fix the n minus 1, become n, this to become n, that to become n. In your attempt to take this to n to n to n, it will also affect this one. So if you do that, what do you end up with? Please mute yourselves. Can you mute yourselves? There is this man called Tumusime. Say easy. Say easy to see me. Tumusime or to see me, say easy. Okay. So what we have is we come here, all that you see here is simply taking that n minus 1, n minus 2, and this n minus 1 to n. So that is what appears next here. That is this work you see here. So when you do that, you can see we have succeeded in achieving that. Now we have n. This is x to the n, this is x to the n, and this is x to the n. Now we have a small problem. That is the limit. This one runs from 0, this one runs from 0, this runs from 0. But the problem is this one runs from 1. Now we can't take this one to 0. No, because when you take it to 0, it will now mess up this power here. So the only option is to take this, this, and this to 1. So we'll upgrade these ones. So that instead of the limit running from 0, it runs from 1 to infinity. This one should run from 1 to infinity, and this one should also run from 1 to infinity. So that all of the lower limits run from 1. If this one here wouldn't mess up this power here, we would definitely have simply taken this to run from 0, and then it becomes, we align it with these ones here. But unfortunately, doing that, I've said it will mess up the power there. So it's better we take these ones. And when you do that, you end up with what we have here now. So you can see this one is running from 1. All of these are now running from 1. You simply throw in n is equal to 0. If you throw in n is equal to 0, you can see this one, you've maintained it. Now this one runs from 1, this one runs from 1, and this one runs from 1. Just throw in n is equal to 0. And once you have that, you can now have this whole statement, and we can now simplify this here. So what do we end up with? We have this one here, and we are saying, and all the coefficients of x to the n to the 0 gives that. Then we compare coefficients. When we compare coefficients here, based on 18, we go on, and we have this statement here. That is when you sum and you substitute, you have this one here, and you have that there. And this is in terms of N0 and L1. Remember from the easy one, guys, rather from engineering math 1, we said if something is of second order, you can have 2 linearly independent solutions. And the 2 linearly independent solutions would mean that your general solution will be something like C1 Y1 plus C2 Y2, where Y1 and Y2, those are of course the two different linearly independent solutions. So in this case, what we have, what we call the C1 is the N0, N0 Y1, but of course Y1 is in terms of X. You people mute yourselves. Kasirie, I don't know what's wrong with this man, Henry. Kasirie, can you mute yourself? Kasirie. Kasirie, mute yourself. This is plus. This is plus C2, but this C2 this time it is L1, Y2, of course, Y2 in terms of X. Why? We are dealing with a second order, so you have N0 into this one here, and then you have L1 into that one there. That's why we are saying, and the two linearly independent solutions, you just pick them from here and here. That is what I've demonstrated, that this is Y2, this is Y1. These ones, they are still fresh in your heads. We did last semester. So you end up with that one there. Is that okay? So from that, is there any question about that? Questions, guys? Questions? Maybe you have a chance to ask. Any question? There is nothing in the chat room. Good, if there are no questions. Since there are no questions, that is very good. We do the very last example. Let us do the very last example and we finish. You see, they gave us our session up to 5, so we can do the very last example. That is this number A. Is this man in Mulindwa running away with my example? Mulindwa. It is this one here. That is number 4. Now, number 4 is a little bit different from what we have been doing. Why? The difference between number 4 and the previous ones, according to the previous ones, everything was taken at X going to 0. If you remember, this was number 3, X was 0. If you recall, guys, then number 2 was also X 0. And number 1 was also X 0. That is what we had. So since that is what we had, in this case, for number 4, what we have as our number 4 here, okay, this is here. This is the one we have. This is number 4. Number 4, this time X is equal to 1. So that is the key. That is one major difference. So you can see we are saying, since we are solving by power series method, about X naught is equal to 1. Remember, initially, in the first 3 examples, the X naught was a 0, this one. But this time it is 1. So we are maintaining the X minus 1. That's why you see it is now X minus 1. So here we can have a change of variable. To simplify this, remember we have been dealing with the n x to the n. So the easiest way here is simply to have a change of variable, and you say if t is equal to x minus 1. So that if you change this now, you will have n t to the n, then the other same methods apply. So where we have x minus 1, we can have a change of variable to a t. And once you have a change of variable to a t, everything changes to t. You solve in t. In the final step, you bring back the x minus 1. So that is all. There is basically nothing much that is new that we are adding there. So just a demonstration that can end in 5 minutes. So we have y, which is sum of this, which is that one there. But x minus 1 can be taken to a t. That is what we are talking about here. That is this part here. That if t is x minus 1, this x minus 1, we take it to a t. Then once we have that, we have y, which is a sum. You can see this one here. Then we differentiate this one twice. That is n t minus 1. The n must run from 1 for this not to go to 0. Then this one, the same story, x has become t. N must run from 2 to avoid this thing going to 0. And now what happens next is the same already story we have been playing with. So with that, since you have this here, you do the necessary changes. So we can substitute. But remember, again, in here we have 2 into x minus 1. But remember the x minus 1 is t. So instead of 2x minus 1, this will be simply a 2t here into y prime. Hopefully we are together there. Because remember, when you take x minus, then it means this x minus 1 must become t. Right. Okay. So that's what we are now doing here. So when we do that, this 2x minus 1 becomes 2t. That is why you see here we have now a 2t right here. This is y prime prime. And our y prime prime has become minus 2x minus 1, but x minus 1 is t. That is the minus 2t, y prime plus 2y. Here, same story. We differentiated it twice. You substitute those derivatives there. The 2t, this t goes inside here. You see that t? We take it inside. When you take this t inside, remember this is t to the n minus 2. This is t to the power 1. You multiply that by t to the power 1. This becomes t to the power n minus 1. That is what it becomes. When you take this t inside here. And you can see when you do that, I don't see the n minus 1. This comes in as 1, so you remain with t. Don't we have a mistake here? Okay, when you substitute, you have that. So this is this is before we change the variable. No, this is n running from 2, same n running from 2. We have this and we have that. I'm not seeing this reducing, and I am wondering why. Hopefully we don't have a mistake somewhere here. Hopefully, because when you take that t inside, it's minus 1 plus 1, it should become minus 1. I don't see it, but it must be somewhere. We need to check that out. But nonetheless, what we have, I was looking at this step. We have this, which is this. Then we have 2ty prime. I think there is a problem with my y prime. Let me check my y prime. Y prime doesn't seem okay. Where is y prime? Okay. Oh, okay. I've seen the mistake. Guys, check this out. Actually, it is correct. Y prime is here. Y prime is n minus 1. Look at the power there. The power here is t to the n minus 1. If you look at that very well. So that is where the source of problem is. So since this is n minus 1, it implies that this n minus 1 If you come with it somewhere here, it means this is 1 here. That is n minus 1. And when you have n minus 1, remember this is t to the power 1 plus 1. You get this n here. I think we've corrected that one. So the problem is in this one here. Please, you go and you correct this one. This 2 here shouldn't be 2, but it should be a 1. Hopefully we are together on that one there. It shouldn't be a 2, but it should rather be a 1. Hopefully we have it right there. So when you substitute, you see y prime prime, that is n into, by the way, there is a mistake that we need to really fix here. Guys, you need to fix the mistakes. There is just one small mess. The mess is in these powers. You see, this is y prime prime. So our y prime prime is n minus 1, n t to the n minus 2. So this one here has a mistake. This one should be a 2 here. Please, you guys, correct this. I'm hoping you are with me. This one should be a 2. I will use black, I think. This one here should be a 2. That should be t to the n minus 2. Because of this one, y prime prime. That should be n minus 2, this one. Then where you have 2t, this is n minus 1. This should be a 1. I'm hoping you have seen that one. You need to change. You need to change those two. That should be a 2. That should be a 2, and this should be a 1. Hopefully you've seen it, guys. So if you succeed in doing that, then this one shouldn't be a problem. Since this is n2, the 2 comes here, which is that. This one, you take the t in, it will reduce this one to n. We have already seen that. And this is to n. Okay. And if you continue with that, okay, I need to erase this one. Okay. Not there, but rather here. And then we go back here. Okay. So if you do that, you can come and you simplify. The simplification is simple. This is to the n to the n. The only thing you have to worry about, the only thing you have to worry about, guys, will be this power here, this one, which is to the 2, because this is to the n, this is to the n. You know how we change that. So if you change this here, you simply let m be n minus 2. If you do that, this is now fixed. It is to the n. This is also fixed. It is to the n. Are you sure? This is the way they go with the internet young again. Huh? It is okay. Customer babazi. Naye zino powa series baba kati